All right, the wonderful world of statistics. I have a little bit of a love-hate relationship with statistics because when they are done correctly, statistics can be very insightful and you can make a lot of good inferences about something. But I feel like more often than not, we are presented with statistics that weren't found in a very good way. And what we're going to kind of focus on today is the fundamentals of statistics, and then we'll kind of lead into the next couple of sections will be more how can you tell if what you're looking at is what is really going on. And with social media the way that it is, you see statistics thrown at you all of the time. And I would argue that a lot of those aren't accurate and aren't even close to accurate. I love it when people just throw out numbers as if they actually did some experiment to get that percentage, when really it's just their way of saying, I feel like a lot of people. So off of my rant, getting into just kind of the fundamentals here. We'll go kind of fast. There's lots and lots of definitions today. We'll get into more specific things later. So 2 definitions of statistics. Really, it's a science of collecting and interpreting data. But usually when we talk about statistics, we're actually talking about the data itself. Numbers, information that we use to describe something. So for example, there's a guy by the name of Nielsen where is my pen? And a long time ago, he started a system of looking at how many people were watching different TV shows at any given time. And he started giving rankings and ratings to different shows based on his data. So for example, at one point, Nielsen said that 22 million people watched Big Bang Theory one night. Okay, 22 million people. Now, it's absurd to assume that Nielsen actually counted 22 million people watching Big Bang Theory. And that's not usually how statistics work, because usually we want to know information about a whole group of people, but trying to get information from a whole group of people is nearly impossible, especially when you have billions of us on the earth. So what Nielsen is doing is the population that he's interested in. The population is the complete set of people, everyone that you're interested in. So his population that he was looking at are viewers in America. Viewers in America. Don't worry, I can smell. Wow, I can spell, guys. Don't worry about it. The sample, now Nielsen, instead of looking at all 22 million people that were watching it, Nielsen was looking at a group of about 5,000 people. Okay, this is what we call a sample. So instead of looking at everyone watching TV in America, he looked at a sample of 5,000 people watching TV in America. And we'll talk about how you come up with these samples in a little bit. But he looked at those 5,000 people and he wanted to know how many of them are watching Big Bang Theory. And that's what our population parameter is referring to. When it says population parameter, that is, what do we want to know about the entire population? So this entire population, we want to know what they are watching. Okay? We want to know what the entire population is watching. That's our population parameter. But we can't look at the entire population. That's a ridiculous number of people and it'll take a really long time. So instead, we take a sample of the people and we use statistics based on that sample. So the sample statistics, and there's actual definitions down here below that you can copy down, but that is the number of people in our sample that meet our parameter. Okay, so if I want to know who's watching Big Bang, I could look at my sample and say, how many of these people are watching Big Bang Theory? I don't know how many actual people are, but based on this statistic, based on this sample statistic, I can make an inference about the big population. Again, I don't know for certainty that it was 22 million people, but based on this sample, it looks like 22 million people would have been watching Big Bang Theory. All right. So population and sample. For each of the following cases, describe the population, the sample, the population parameters, and the sample statistics. So for part A here, remember my population is the entire group that I'm interested in. So an agricultural inspector measures the levels of residue from 3 common pesticides on 25 ears of corn from each of the 104 corn producing farms in the county. So my population is all of the corn in the county. That's the group. I'm looking for pesticides in all of the corn. So my population is all the corn. My sample, because I can't look at every piece of corn and test it for pesticides, that would be ridiculous. My sample is 25 ears from each of the 104 farms. So my sample is 25 ears of corn from 104 farms. That's a pretty good sample. That's a big sample, and it's coming from multiple farms. It's not just one farm. My population parameter, what I am interested in, what I want to know about the entire population is what are the level of residue? What's the level of residue on the corn? On all of the corn. That's what I'm trying to find out. What's the level of residue on all of the corn? And my sample statistics I'm looking at what's the level of residue on those 25 ears from each. So my sample stat is the level of residue on my corn samples. Not all of the corn, but my corn samples, okay? So anthropologists estimate the average brain size of early Neanderthals in Europe by studying skulls found at 3 sites in southern Europe. Okay, so my population, what I'm interested in is Neanderthals in Europe. What I want to know about them, my population parameter, I'm getting a little bit ahead of myself here, but what I want to know about those Neanderthals is their skull size. How big is their skull? The sample that I use, my sample isn't all of the Neanderthals. It's the skulls found at 3 sites. In southern Europe. So I just look at the skulls that have found at 3 sites. That seems kind of lazy. My sample statistics are going to be the size of the skulls of my sample. What are the size of the skulls of that sample? That's my statistics I'm looking for. And I'm going to use that information to make an inference about the skull size of all the Neanderthals. Okay. All right, moving on. I feel like you guys have seen this stuff enough in the past. We can go a little bit quick. You can always pause and ask questions when we come to class as well. So this one right here, basic steps. There are 5 steps in a statistical study. I want you to pause the video and I want you to read through those 5 steps. I'm not going to take the time over a video to read it to you and to read this example question. But what I want you to do, pause the video, read these 5 steps, and I want you to read and try to answer this question, okay? So take a couple of minutes, pause the video, see if you can answer the questions about that study. Okay, hopefully you have a bunch of information written down here about your answers to that. Now, what I would like you to do is compare what you thought to the actual solution. So go ahead and pause the video again, and I want you to look at each of those steps. Did you have a similar answer? So pause the video and check your work. Okay, we can work on these more in class, but again, doing this over a video, I don't feel like reading through all that is going to be a good use of our time. especially because we have all of this that we want to read through. So choosing a sample, really, this to me is kind of the biggest, most important part of any experiment, is choosing a sample, because the idea is we can't gain statistics, we can't gain information from every person, every ear of corn, every Neanderthal. But if we can find a sample that represents that group, that population correctly, then we can gain some good information. So there are 4 common sampling methods, and they all have their place. Only one of them is terribly bad. But the first one is simple random sampling, and that's where you just randomly choose from the entire population. So that's like taking all of the corn in the county and just randomly picking pieces of corn. Okay, it's just taking all the phone numbers in the phone book and randomly picking 5. It's just complete random of everyone, the entire population. Okay, systematic sampling is when you use a system like, I'm going to ask every 10th person that walks by, or I'm going to go down the phone book and I'm going to call every 50th person in the phone book. There is a system to how you're picking your people. Okay, convenience, this is the one, yikes. We choose a sample that's convenient, like asking the people sitting around you in the classroom, or only asking the people at your school. And sometimes that convenience can be really bad. If you were wanting to know something about students at Dixie High School, it would make sense to choose a sample of students at Dixie High School. But if your population was bigger than that, if your population was, if you wanted to know something about high school students, you can't just ask students at Dixie High School. That would be convenient, but they don't represent high school students in general. They represent our culture, our group of high school students. Okay. Stratified sampling is where you kind of have this big population and there's subgroups of the population. So like maybe that television example, maybe within all of the people watching TV, maybe they wanted to break it up into subgroups, like teenagers. How many teenagers are watching the show and how many adults are watching the show? So they're taking a sample from different subgroups of the population. A really common one in these groups is male and female. Okay, when they want to know something about people, so they take a sample of males and a sample of females. They have 2 subgroups and they take samples of both. That's called stratified sampling. It's kind of just breaking your big population into smaller populations. So number 3, identify the method of sampling. So A, you are conducting a survey of students in a dormitory. You choose your sample by knocking on the door of every 10th room. So your population are students in your dormitory. So you could almost say this was convenient. If they wanted to know something about college students, this would be convenient. But they're only asking about students in their dorm. And so they go and they knock on every 10th door or every 10th room. So this one would be our systematic sampling. They're just knocking on every 10th room out of the group, out of the population of rooms they're interested in. Okay. To survey opinions on a possible property tax, a research firm randomly draws the addresses of 150 homeowners from a public list of all homeowners. So that's just our simple random, right? That's just this first one up here. It just randomly picks out of all of the homeowners. So that's just a simple random sampling that they took. C was the ears of corn one that we talked about. They picked 25 ears of corn from each of the 104 farms. So I would say that this one is stratified because they used each of the farms is kind of our subpopulation, our subgroups, and they took 25 ears from each of the farms. So that would be a stratified sampling. Okay, moving on. I'm going to try not to read through too much of this. We're going to talk about a lot of it, though. There are basically two types of study. They're pretty self-explanatory. An observational study, you observe and measure stuff that you observe. You don't try to change things or modify or introduce something. You just watch and measure what you see. Okay, in an experiment, tongue tie there, you are affecting the outcome because you're applying a treatment to one of the groups and you're watching what the effects are from that treatment. Okay, so you're not just watching anymore, you're introducing something to affect the outcome. Now, one thing we've got to be really careful of when you are doing an experiment, which is mostly what we're going to talk about today. We're not going to talk about much of the observations. When you're doing an experiment, it's really important, guys, it's one of those days. It's really important that you have these two specific groups, okay? You have your treatment group and you have your control group, okay? Now, the treatment group are the ones that are being modified. They are getting the medicine. They are using a new shampoo. They are the ones that are being affected with whatever you are experimenting. Okay. So these ones, well, it's just what it says. They are getting the treatment. Okay. The control group, and here's where you have to be careful. It's important that the control group thinks that they are getting the treatment. They think they are getting the treatment, but they're not. This group is not getting whatever treatment the other group is, but it's important that they think they are. And we call that the placebo effect. That's down here in definition. You can pause, you can write this all down word for word. But the control group is getting a placebo, which remember it kind of acts, it's kind of like a fake treatment. For example, if you were giving a lot of high school students will do kind of studies on pain pills when they get their wisdom teeth out. And some of the kids get their wisdom teeth out and they get this new pain medication. The other group, the control group, gets a placebo. They think they're getting the pain medication, but they're actually getting something else. And it can't be a different medicine. And here's where we've got to be really careful. The placebo can't be a different kind of pain medicine. The placebo has to just be fake medicine. You can't give them a different medicine. You have to give them what they think is the same medicine, but it's actually not medicine at all. Okay. And that's where we have to be really careful with placebos. And there's all kinds of effects that happen with placebo. There's all kinds of studies that they do on how much the placebo effect actually influences people. And most of the studies come out to show that there's some pretty strong proof that sometimes people just thinking they're getting medicine makes them get better. In their head, they're getting the medicine. They shouldn't hurt as much. And so they can convince themselves that it doesn't hurt as much because they think that they're getting the medicine. Okay. Now, here's the other important part of a study. And here's one that, especially in medicine and research, they're really picky about. Who knows who is getting what? In a single blind study, what that means is that the participant doesn't know if they're getting the treatment or the placebo. They don't know, but the experimenters do know if they are giving them a treatment or a fake treatment. And that's kind of scary to do, especially when you're dealing with medicine, because there could be a lot of reasons why the person doing the experiment might want someone to get the treatment. Maybe they know that person, or maybe they like that person and they want them to get the treatment so they get better. Whereas maybe there's someone they don't care about or they're not as interested in, and they don't care if they get the treatment or not. So single blind sometimes is appropriate, but in a lot of situations, that single blindedness can alter the way an experiment comes out, which is why a lot of experiments, especially when we're dealing with medicine and psychological things, are double blind. And what that means is the people getting the treatment don't know if they're getting it for real or if they're getting a placebo. But also the people who are doing the study don't know who is who. Or in other words, they don't know if they just gave a person a placebo or if they just gave a person the actual medicine. And that's really important when you start to analyze the data. And that's really important when it comes to not influencing the results based on what you hope happens. Okay. So a couple examples with this, and then that's probably going to call it for the day. What's wrong with these experiments? So for each of these experiments, identify the problem. So in a chiropractor performs adjustments on 25 patients with back pain. Afterward, 18 patients say that they feel better. The chiropractor concludes that the adjustments are an effective treatment. So to me, the first problem with this experiment is he's looking at 25 patients and he gave all 25 patients the same treatment. There wasn't a control group. There's no control group that thinks they're getting the treatment, but they're not. You only have 25 people getting the treatment. And the problem there is some of those 18 might be getting better because of the placebo effect. They might just be getting better because they feel like they should be getting better. Some of those 18 might actually be getting better because of the treatment. They might also be getting better just because they're getting better on their own, whether or not they got the treatment. So when you're only looking at the people you gave the treatment to, that causes a lot of problems. So how could that have been avoided? A few different ways. The problem is you have to have a control group that thinks they're getting the treatment. So you could have another chiropractor, or you could even hire someone to pretend to be a chiropractor that does a fake treatment on the person. So instead of actually adjusting their back, they might just pretend to be adjusting their back. They may be doing things that makes the person think they're actually adjusting their back, but they're not actually making any changes at all. Okay. So A definitely needs a control group. You can't say that that is effective. It's kind of like that false cause that we've talked about. That right there would be a fallacy. Just because 18 people got better doesn't mean it's because of your treatment. You don't have another group to compare that to. B says a new drug for a type of attention disorder is supposed to make children less disruptive. Randomly selected children suffering from the disorder are divided into treatment and control groups. So they have the two groups, the treatment and the control. Those in the control group get a placebo that looks like the real drug. That's a good start. The experiment is single blind. And I'll tell you right now, that's going to end up being the problem. Experimenters interview the children individually to decide whether they become more polite. So here's the problem to me. The experimenters know who should be getting more polite. Okay. The experimenters want this study to go well. They want the medicine to work because that means they are going to make money selling the medicine. So when they're talking to these two groups of people, they've got the treatment group that they want to be polite. And they have the control group that they don't want to. They would rather see the control group not be polite because that means this group looks like it's working better. So this is a huge problem because they might talk different to the children. They might treat them different. They may word the questions in a different way to get different responses. The fact that they're looking for them to be polite, that's a really easy thing to alter with children, because if you're ignorant and ornery and rude to a child, you're going to get a lot of that back. Whereas if you are patient and kind, they're probably going to be more polite back to you. So this study definitely should have been a double blind. Okay, those interviewers, even if the experimenters know, the people doing the interviews can't know if the person is from the control group or the treatment group. There's way too many examples of that getting going the wrong direction. Okay. And then the last topic here, margin of error. So there is, and that's one thing that maybe we should have mentioned back when we were talking about samples. Okay. We have all of these different samples, and theoretically, you could take a large sample in a bad way. You could ask every student in your class about what they think about high school, but you're still taking, that's a large sample of a convenient group of people. Or you could take a small sample that were well chosen that might represent your population better. So there's ways that you can influence these samplings. And more than that, just because it is supposed to represent the population, and I can't stress this enough, just because theoretically it should, doesn't mean that it will. Okay, so for example, before we get into this margin of error, let's say that I want to know, I want to interview college students that what is their average height? I don't know. What's the average height of a college student? Okay. Now, if I go and ask the basketball team or the girls volleyball team what their heights are, that's going to be totally biased, because usually basketball players and volleyball players are taller than an average student. So in theory, what if I just selected 100 random students? What if I just had the entire list of students at the school and I randomly selected 100 students? Now, theoretically, because I selected them randomly, that should be a good population. And I emphasize the word should be. Okay? That is the best chance I have of having a good sample. That does not mean it is guaranteed to be a good sample. Because if I'm randomly, let's say there's 1,000 students in the school and I randomly pick 1 out of 1,000, that student is just as likely to be a volleyball player or a basketball player or anyone else from the school. And then I select another person, but now I only have 999 to choose from. Theoretically, that could be anyone, but because we're selecting randomly, it could be another basketball player. And then I select another student. Theoretically, it should be a random student, but because it's random, I could accidentally randomly pick another volleyball player. So the problem with, I guess not the problem with samples, but the thing that you need to keep in mind is it is a sample. It's a random sample, whatever way you chose your sample. It should represent the population if it's done correctly, but that doesn't mean it absolutely will. That just means that it should, okay? And that's where we get to margin of error. So what a margin of error says is it basically assigns how accurate they think that that sample statistic is. And I like that they do this, and we'll get into the math of it a little bit later. But basically what they say is, we believe that this is a statistic. So for example, an election eve poll finds that 52% of voters plan to vote for Smith. So they take this poll and they believe, based on their sample of people, that 52% are going to vote for Smith. Well, that's what they believe. The problem is, there's always a chance that that 52% that you got wasn't the best sample. There is room for error in that. And so what statistics usually will come with, if they're done correctly, is they'll say that there's a margin of error in the poll that is 3 percentage points. Now, what that means is the poll says 52%, but there's a margin of error of 3%, which means it could actually be up to 55%. It could be 3% higher than what they thought. It could also be 3% lower. It could be down at 49%. So that confidence interval, what it's saying is they are confident that it is within this range. okay? Because there's this margin of error of 3%. They'll say 52%, but they're confident that it's somewhere between 49 and 55%. Okay, that seems all right. But when you're looking at a question like this one, can we assume that Smith is going to win the vote? Well, she needs to get 50% to win, but we believe that she is somewhere between 49 and 55%. So I would argue that that is too close to call. That she has to have more than 50%, because if I'm between 49 and 55, that means two of those numbers, the 49 and the 50, she loses. And that only gives me four numbers where she wins at 51, 52, 53, 54, and I guess up to 55. So I wouldn't argue that we are confident or that we should assume she could win, because my margin of error, this is just as likely as this one to happen. Okay. So we've got to be really careful when we're looking at statistics, what that margin of error is. And if you are about to make a life decision based on a statistic, you better know how confident what that interval is. Because if they tell you that 70% of people that spend their money on this car are satisfied, but the margin of error is 10%, that means somewhere between 60 and 80% of people are happy with their car. Well, if it's this end of that interval, that's just a little more than half. I know this looks really good, but what if it's at this end? That margin of error goes both ways. So that confidence interval, it's really important that that is a small interval. The better the statistics, or the better the sample, the better way the experiment is ran, the smaller that interval is going to be, the closer you're going to get to what you're actually looking for. Okay, so what you should be working on, big old 5A, right? So homework 5A, you can start that at home. If you have questions, bring them to class. We'll work on those questions in class together. And then we'll kind of move on into some more of the math and behind the scenes stuff when it comes to all the statistics.